Hello, welcome to part 3 of this lesson on projectiles. In parts 1 and 2 we looked at horizontal projectiles and how to do calculations involving them. I'm assuming you've seen and understood both those parts. In part 3 we're going to take what we've learned and extend it to non-horizontal projectiles. That means ones fired at any angle, for example the one in the diagram at the top. As always, a pen, paper and calculator will let you try the exercises as we work through the lesson. So if you want to go and get them, now is a good time to pause. A quick word of warning. There will be some mathematics involved. You need to be able to resolve a vector, in this case velocity, into its components. You also need to be able to solve a quadratic equation and do some fairly messy arithmetic on a calculator. There is a separate lesson about resolving velocity into components if you need to watch that. Let's make a start. Here's a diagram showing a projectile. The initial velocity, white arrow, I've called u, 10 meters per second. And the initial velocity when you maybe throw the stone is at an angle of 60 degrees to the horizontal, and the red line shows the trajectory, the path, and if there's no air resistance it will be a parabola. The distance it travels is called the range. We often have to calculate the range. Okay, let's take a careful look at this initial velocity. It's 10 meters per second at 60 degrees to the horizontal. I've drawn a little construction box there to help you. Can you pause the video and work out the horizontal and vertical components of that initial velocity u? What is the horizontal component? Yellow arrow. What is the vertical component? Blue arrow. Pause, see if you can do that. Well, I hope you've tried it. You don't really need to draw the box, but it might help you. The horizontal component is 10 times cos 60 degrees. Cos 60 is half, so it comes to 5 meters per second. That's the horizontal component of velocity. What about the vertical one? Well, u subscript v is 10 sine 60, comes to 8.66 meters per second. And as I mentioned a moment ago, if you don't know how to do that, you may want to watch a separate lesson on how to resolve a vector into components. So we've got these two components of velocity here, the horizontal and vertical. Those are the values at the moment the thing is launched. And I hope you remember from what we learnt about horizontal projectiles that this horizontal velocity, 5 meters per second, is actually constant. As the thing moves through the air, the horizontal component of velocity stays 5 meters per second, but the vertical component will change. Let's take a look at the vertical component of velocity in more detail. There's our diagram. The initial vertical component of velocity is 8.66 meters per second. Now, let's imagine we throw up another object at the same moment that we launch the red ball. And this second object, launched at the same time, is going to have some vertical velocity. It's actually going to be thrown vertically upwards. And we're going to make its vertical velocity, its entire velocity initially, 8.66 meters per second. So it's got the same vertical velocity as the vertical component of the red ball, both 8.66 meters per second. And we're going to throw these two things up together. Let's just summarize what we're doing. The blue ball is thrown vertically upwards at the same moment as the red ball is launched. And the initial velocity of the blue ball is the same as the vertical component of the red ball's velocity. They're both 8.66 meters per second. Very important. And let me ask you, what do you think will happen? What do you think we can say about the behaviour of the red and the blue ball? Pause and just think about that for yourself. Well, I hope you've thought about it. What we can say is what we say at the bottom. The vertical motions are identical. They were launched together with the same vertical velocity. They'll have the same heights and the same vertical velocities at later times. So, for example, when the blue ball is at that height, the red ball will be at the same height. When the blue ball is at maximum height, the red ball will be at maximum height. And on the way down, they stay together and they will hit the ground together. At any moment, they will have the same vertical velocity. At the top, for example, the blue ball has a 0 vertical velocity, maximum height. The red ball has a vertical component of velocity, which is 0. Of course, the horizontal component is still 5 meters per second, but we're only considering the vertical motion. It's the same as an object thrown straight upwards with the same vertical speed. That is very important to understand. Let's summarize these points that we've just covered. There's a projectile's trajectory, and whenever we want to solve projectile problems, two very important things you have to remember are the horizontal component of velocity is constant. That's because there's no force in the horizontal direction, so the velocity stays constant. No force means no acceleration, assuming no air resistance. And the other thing you must remember is the height and the vertical component of velocity are the same as for an object moving only vertically that had the same initial vertical velocity. Might want to pause and read through that. Very important points that we use over and over again when solving projectile problems. Okay, here's an exercise for you. We often have to work out how long something is in the air for a vertically thrown object or for a projectile at an angle. So here's your first exercise. How long does a ball thrown vertically upwards at 8.66 meters per second take to return to its starting position, starting height? As always, g 9.8 meters per second squared. You can ignore air resistance. Now there are 3 different ways to do this. I'm going to go over all 3 ways in a moment, but any way you can you work out how long this ball is in the air? Pause the video, try this for yourself. Okay, let's go through it. Here's one way. We could find the time it takes to reach the maximum height and then double it because it takes the same time to go down as it did to get up there. Symmetrical. Let's use one of our Suvat equations. V is u plus at. At the maximum height, the final velocity v is 0. It's stationary instantaneously at the maximum height. Talking about vertical velocity. The initial velocity was 8.66 meters per second. Take upwards as positive. The acceleration is g minus 9.8 meters per second squared as it's downwards. Let's put some numbers in. Final velocity u 9.8 with a minus sign. Do the arithmetic, rearrange it, and we get the time it takes to get from when it's thrown to the maximum height is 0.884 seconds. And when it comes down, it's symmetrical. It takes the same time to get down. So just double that. Time to fall down is the same. The total time it's in the air is twice 0.884, which is 1.77 seconds. That's a fairly straightforward way to do it. Let me show you a couple of other ways that are useful to know about. Let's think about the initial and final vertical velocities. We know the initial velocity is 8.66 meters per second upwards. When it comes back down to its starting point, what will be the final vertical velocity? Well, I hope you can tell that it's going to be minus 8.66 meters per second. The same speed, but the direction has changed. It's conservation of energy. If it has certain kinetic energy at the start, it will have the same kinetic energy at the end. So if there's no air resistance, the speeds will be the same. It'll be going at minus 8.66 meters per second when it comes back. Well, let's use our Suvat equation v is u plus at. If we do the whole journey, when it lands, when it comes back to its starting position, v is minus 8.66. The initial velocity was 8.66 upwards. At is minus 9.8t. Do the arithmetic and you get the same answer, of course, as we did a moment ago. It's 1.77 seconds. So that's another quite neat way to do it. Is there another way? Yes, there is. Let's use the vertical displacement. If it goes up and comes back to its starting position, what's its displacement? Well, I hope you know it's 0. Here's another Suvat equation. The displacement is 0. Let's put some numbers in. If it comes back to its starting point, displacement is 0. U was 8.66, so it's 8.66t plus half gt squared, that's minus 9.8t squared. Let's rearrange that, and we get a t squared term on the left side and the t on the right. The t's will cancel out on both sides to leave t is 8.66 over 4.9, and no surprise, it comes to 1.77 seconds. So that's quite a neat way to do it, and this could be very useful if it returns to a different height. If the thing is thrown up and then lands at a different height above or below its starting point, this third method shown in yellow could give us a very easy way to find the time it's in the air. The important point is you need to be able to find out how long something is in the air by considering the vertical velocity, the vertical motion. Now, here's an entire problem for you. Here's our projectile, initial velocity 10 meters per second at an angle of 60 degrees to the horizontal. Can you now do the whole problem? Can you find what the hang time is? That just means the time it's in the air. And then can you find the range? How far does it travel horizontally? Pause the video, see if you can do the whole thing. Well, I hope you've had a go. If I were doing it, the first thing I would do is this. Work out the horizontal component of velocity. We've already done it earlier, but this is what we're doing now. Work out the vertical component of velocity. This is what you would write down if you were solving the problem. What about the hang time? Well, we've already worked it out. Let's just repeat the calculation though. We can use v is u plus at. Let's use the final and vertical components of velocity. Now remember, this projectile in the vertical direction behaves just the same as something thrown vertically up and coming down. So we can do exactly what we did a minute or two ago and consider the vertical velocity. The vertical component of velocity when it comes back to the ground is minus 8.66. The initial vertical component of velocity was 8.66. At is minus 9.8t. It's just the same calculation as for something thrown vertically upwards. The fact it's moving sideways at the same time doesn't matter. The vertical motion is the same as an object thrown vertically. It's the same calculation as we did a moment ago. And when we do it, it'll come to 1.77 seconds. That's the hang time. What's the range? Well, in the horizontal direction, the velocity is constant. It's a steady speed, if you like. So we can say that distance is speed times time. The range is the horizontal speed, which is constant, times the time it's moving through the air, which is the hang time. So it's 5 horizontal component of velocity times the hang time, 1.77 seconds, comes to 8.85 meters. We've worked out the range of this projectile. This is the basic calculation we have to do for most projectile calculations, simple ones anyway. So it's very important you understand exactly what we've done and why we've done it. If you need to pause the video, read through that for yourself, think about it, now is a good time. Okay, we're going to do another couple of problems. If you're starting to get tired, by the way, you can always pause the video and go and get yourself a cup of tea or coffee, because this is a relatively long video and there's a lot of messy arithmetic and things like that. But if you're okay to continue, here goes with the next problem. I want you to do exactly the same type of calculation as we've done a moment ago. Just different figures. I just want you to practice the technique. So here's question 2. A cannonball is fired at 110 meters per second at 40 degrees to the horizontal. You ignore a resistance. You take g as 9.8 meters per second squared. And the question, well, there's 2 parts. Find how far away it lands. That's the range. And sketch the trajectory. That's the path. If air resistance is not negligible. If you can't ignore air resistance. So 2 things for you to think about. Pause the video, try that whole thing for yourself. Well, I hope you've tried that. Let's go through it. I would start by working out the initial vertical and horizontal components. U subscript H, that's the horizontal component, will be 110 cos 40 degrees. 84.26 meters per second. The vertical component of velocity should work out to be 70.71 meters per second. So we know those initial components. Now we're going to work out the hang time. It hasn't asked you to work it out, but I hope you realise to find the range you need the hang time. Let's do the hang time. Let's use V as U plus AT. Let's think about the initial and final vertical components of velocity, remembering the thing behaves just the same as something thrown vertically up and coming down. Let's use V equals U plus AT, considering the vertical components of velocity only. Well, the final vertical component of velocity when it comes back to the ground will be minus 70.71. The initial vertical component was 70.71, AT is minus 9.8t. Do the arithmetic and you get 14.43 seconds. That's an intermediate step. So we know the hang time. It's been moving through the air for 14.43 seconds. We were asked to find how far away it lands, the range. Let's do that. In the horizontal direction, the range is simply distance is speed times time. It's a steady speed of 84.26 meters per second for a time of 14.43 seconds. Stick the numbers in, round the answer probably to 2 significant figures, same as the data supplied, 1200 meters. Standard, classic problem. If you can do that, you can do many projectile problems. Some are a bit more complicated. So to finish off, let's do one slightly harder projectile problem. Oh, I haven't done part B yet. Sketch the trajectory if air resistance is not negligible. What did you do? Let's remove that to make it clearer. If there's some air resistance, it will affect the trajectory. Something like this, perhaps. The purple line. You'll notice a couple of things, 3 things in fact. First of all, the range is reduced because of air resistance. The maximum height is reduced. And this shape actually isn't a parabola. It's not a symmetrical curve about a vertical axis. It's squashed more on the right hand side. So air resistance has that sort of effect. To work it out, do calculations involving it, is quite tricky and involves calculus, and we're not going to look at that now. Okay, one more question for you to try for yourself. Let me read it to you. A ball is thrown at 12 meters per second and 70 degrees to the horizontal from the edge of a 20 meter high building. How far from the base of the building does it land? Take G as 9.8 meters per second squared. Air resistance is negligible. The first thing I want you to do is draw a suitable diagram. Always draw a diagram to help you formulate the problem in your own mind. So pause and have a go at the diagram now. And I hope you've done something a bit like this. I've decided just for a bit of variety to go right to left. You may have done it left to right. It doesn't really matter. This ball is thrown at 12 meters per second. We can draw an arrow representing it. Right 12 meters per second next to the arrow. You can show the trajectory. The building is this blue block here. The height of the building, the height from which it's thrown is 20 meters. Put that on. We want the range, how far from the base of the building it lands. So a diagram like that would be suitable. You don't need to draw a box to show the components. You ought to be able to work out horizontal and vertical components straight away without drawing a diagram. With a bit of practice, it's pretty easy. So now we've got a diagram. Pause the video and see if you can do the rest of the problem for yourself. Well, let's see. I hope you had a go. There's the diagram again. The first thing I would do is work out the horizontal and vertical components, the initial components of velocity at the point of launch. UH is 12 cos 70 and UV is 12 sin 70. So we know the components. We want to know the range. So the first step is to get the hang time, how long the thing is in the air. Now, this is a bit awkward. There are a couple of ways to do it, but it doesn't return to the same height it started from. It's actually gone up and then down, and then a further 20 meters in a vertically downwards direction. Let's see if we can work out the hang time. And I'll show you two methods. Let's start with one of our Suvat equations. S, well, in the vertical direction it started at the top of the building, and at the end of the motion it was at a level 20 meters below that. So that would mean S is minus 20. In the in-between time it had a constant acceleration, being slowed down and then accelerated downwards. But the displacement overall is minus 20. Let's put some numbers in. S is minus 20 meters. U was 11.28 meters per second, vertical component at launch. Remember, we're only looking at the vertical component of velocity. Forget about the horizontal component. Think only about vertical motion up and down. So we've got ut is 11.28 t. Half at squared will be half minus 9.8 t squared. Let's rearrange that and make it a bit neater, and rearrange it to be in the standard format that we use for quadratic equations, because we have ended up with a quadratic equation. Instead of x we've got t, but that doesn't matter, it's a quadratic equation. I hope you remember how to solve quadratic equations. There's the diagram again just for reference. There's our equation on the top. To solve a quadratic equation, hope you recognise the expression minus b plus or minus the square root of b squared minus 4ac all over 2a. A, b and c are these coefficients. A is 4.9, b is minus 11.28, c is minus 20. We've just got to put the numbers into the standard formula for the quadratic solutions. Let's do that. I'm not going to read it out in detail. You can pause the video and check if you want. Becomes that, and it eventually becomes 11.28 plus or minus 22.79 over 9.8, and that gives us two solutions. We can do 11.28 plus 22.79 all divided by 9.8, or we could do 11.28 minus 22.79 over 9.8. We'll get two solutions, 3.48 seconds or minus 1.17 seconds. And we say that the negative solution isn't physically meaningful. It actually refers to the time before launch that this projectile would have been at ground level here. But let's not worry about that. We just can say we can ignore the negative time as it's not physically meaningful in this problem. The answer is it's in the air for 3.48 seconds. It goes up and comes down again. That whole thing takes 3.48 seconds. Now, is there a way to do that if we don't like solving quadratic equations? Well, there is. Let me show you another way to get the hang time without having to solve a quadratic equation. But don't lose track of the fact that what we're doing is just considering the vertical motion alone, the vertical components of velocity, to find out how long it takes to go up and down. But here's another method. Let's find the vertical component of velocity on landing. So we know when we launch the thing it's going upwards at 11.28 meters per second. when it lands it will be going downwards faster than that because it's got some extra distance to fall. It will gain some kinetic energy, losing potential energy. To find the vertical component, let's use another Suvat equation. V squared is u squared plus 2as, where v is the final vertical velocity. Again, don't forget we're only thinking about the vertical components of velocity. We're ignoring the horizontal motion. Let's put some numbers in. V squared is, well, the initial vertical velocity u is 11.28, so it's 11.28 squared, 2as, 2 times minus 9.8, and the displacement is minus 20 because it's finished 20 meters below the start point. Up positive, down negative. So be careful about the signs. And when we solve that, we'll get v is plus or minus 22.78 meters per second. You can try that for yourself. We know it's going downwards, so we know v has to be negative. So we'll use the negative square root, minus 22.78 meters per second. Now, what that means is, in the vertical sense, it was moving upwards at 11.28 meters per second, and it finished moving downwards at it started moving 11.28 meters per second upwards when we launched, and it finished moving 22.78 meters per second downwards when it hits the ground. We can use those figures to get the time. V is u plus at. Again, just considering the vertical velocity, the final velocity when it hits the ground was minus 22.78. The initial vertical velocity was 11.28, and at will be minus 9.8 times t. And it's not a quadratic equation. We can just rearrange it and get 3.48 seconds, same as we got by solving the quadratic equation. So we know the hang time. There are two ways to get it. To get the range, the last bit is easy. The horizontal velocity was 4.1 meters per second, and that was constant. So it was moving horizontally at 4.1 meters per second, and that didn't change. The range distance is speed times time. The horizontal speed is steady, so it's moving at 4.1 meters per second for 3.48 seconds. Distance is speed times time, 14.3 meters. Pretty straightforward in the end, but some messy arithmetic we have to work through. Nearly done. Just one thing I'd like to mention. You should know this if you're learning about projectiles. Here's a question. For a given initial speed, for example, suppose you can throw a stone at 10 meters per second, at what angle should you throw it, the projectile, so it goes as far as possible, assuming no air resistance? What distance should you throw it to make it go as far as possible? And I'm not going to ask you to work it out because it's a little bit of messy mathematics which we're not going to go through, but the answer that you ought to know is it's 45 degrees to the horizontal. You can do it using calculus, you can do it with a bit of trigonometry, but I'm not going to bother. I'm just telling you this very useful result. If air resistance can be neglected, to get the maximum range when you throw something, throw it at 45 degrees to the horizontal. And if air resistance is significant, you have to reduce the angle. There's the diagram. Maximum range 45 degrees. That's it. And there are much more complicated problems that can be asked about projectiles, but I'm not going to look at those here. I wanted you to understand the basics, and if you've understood everything in the three parts of the lesson, you have a very good grasp of the basics that you might need for more complicated material. Thank you for watching.